last two times, the first two lectures I gave, I spoke to you about geometry, and this was geometry about mostly plane, the two-dimensional real vector space R2, and how that relates to groups, and we studied the group of affine transformations, and we saw some nice things about that. And it made us, at the end of my second lecture, I indicated that there is a strong relation between geometric structures on R2 and subgroups of the group of all permutations of R2, bijective maps from R2 to R2 that leave invariant certain things like the collection of all lines. They are nice subgroups. Okay, so now we change completely. When I was part in organizing this school, I thought what would be a nice geometric goal to do. And good. So what I came up with was a Fourier analysis on the two-sphere. So the two-sphere, this is the sphere in R3 of dimension 2. So I think that would, does that look like a sphere? Does it make it more or less clear? It's like the surface of the Earth, right? So most mathematics is very, in an ideal world, the mathematical world, and there things are easy and clear and well-defined and ideal. A line is infinite, and in the practical world where we live, that's not the case, but I wanted to do something with an application to the real world. And so I wanted to do analysis, harmonic analysis it is called, on an object like this. And that is what the other 4 lectures are about. So today, this is an example of what, you want to do analysis on something that is not just like R2, right? This, or R3, but not an open subset of R3. You cannot, if you take your first analysis course, nobody tells you how take derivatives of functions on this thing, or how to do a volume integral, or so we have, that is what we want to do. And so we want to first do something about manifolds, and then what is called Lie groups. So symmetries, this has a lot of symmetries, all the rotations in, you put this in R3, the origin is the center of this sphere, then all the rotations outlined through the origin observe this sphere. And that is the group of symmetries of this sphere. If we do not allow things of determinant minus 1, that change the orientation. Related to the topic of the school, groups and group actions in arithmetic and geometry. But maybe I put it a bit higher somehow. So, is this better? Yeah. Okay, good. I should talk a bit down. So the group is not a finite group. But so in order to work with this group of all rotations, we have to describe it as a Lie group. And a Lie group is a group that has also a manifold structure like also this sphere. So we have to do a bit more geometry with groups. And these groups are much bigger than the finite groups, but this group of rotations happens to be compact, which is good because then it is still small in some size, in sense, and that makes it possible to apply a generalization of what we will see in the course of Laura and René on representations of finite groups to this group, and we get, in the end, formulas, say the analogs of the basis functions this two-sphere from just symmetry. That was my goal. And so then I remembered that a long time ago, in 2006, I had a bachelor student in my department who wrote a bachelor thesis about this. So, but that was in Dutch. So I spent a few days of my Christmas vacation translating this bachelor thesis into English with permission of the author. So, and this became these notes, and you can find these notes, I hope you already found them, on the website of the school. If you go to discourse, you find these notes. So this is the bachelor thesis, bachelor science thesis. It is from 2006, and it was supervised by 3 people, among them myself, and I did the least, but translated by me. And if you see mistakes still in this thesis, then please tell me, we can improve the notes. Okay, and so today we do sections 1 and 2. So in the like 45 minutes that I have. So you see, this is not very reasonable. I cannot copy, and also I would not want to project these notes on the screen because then we have to go very fast. What you have to do is to take some time and read these notes yourself. Yeah? And I tell you only the most important things in these notes. So what is the most important thing in section 1? This is about manifolds. And so, yeah, I have no idea how many of you have already seen the notion of manifolds. And does it make sense to ask it? Could everybody who has seen manifolds already somewhere in his or her curriculum raise his hand, her hand? I see there a few, but yeah, not much. Huh? So I really advise you to read these notes. And I will give you, I think in mathematics, we have something that all the other sciences, almost all the other sciences don't have, that is definitions. And I think definitions are the most important things. So what is a manifold, right? And let me take half, maybe until 10 o'clock, to tell you about manifolds. And then I will switch to section 2. So here, definition. Well, maybe to write officially a definition is a bit cumbersome. So I will just write a bit more like a story. Well, maybe I should, okay, let X be a topological space. So that means that X, and I assume that you know what this is, but if you don't, then just try to survive this course and ask me in the break or at some point what is a topological space, or ask your neighbor actually, that is even more productive probably. So if you want to do analysis on this object, but you can only do analysis in R2, say, then you should say, well, locally I can parameterize this with a subset of R2, with an open subset of R2. Suppose I would project this two-sphere on the xy plane. So I just say, well, here is the z coordinate axis, it goes through it, and here is another coordinate axis, and here is another one. Right, so now it is fixed in my 3D space. Maybe also here dashed line, and here is then the origin where these 3 intersect. I could project it on the xy plane, and then everything that is north of the equator, that is an open subset. If I take everything that is strictly above the equator, so, and I look at how that projects, that is a bijection. And I could say, well, that gives me coordinates on this on that part. If I would like to do it on the equator, including the equator, it is bijection, but you see that the projection has derivative 0 on the equator because the tangent is, well, the vertical lines are tangent lines, and that is very dangerous. You don't want that. You want that this derivative here would be invertible. So on each, yeah, I think I could say, well, on such a part that everything that is above the equator, I know how to make coordinates, and that is the idea. So X a topological space, a chart at X in X, so I take a point, is a homeomorphism. Say phi from, well, now I should, yeah, I'm not going to look at these notes, okay? So it may very well be that in the notes the notation is different because ux to vx, this ux is an open subset of x. This is, remember that this X is a topological space, so I know what are open subsets. I want an open subset that contains the point X, and it should be a homeomorphism to Vx, which is an open in A, in R to the something, right? So a chart at X in this of dimension, well, or I should say a dimension D chart. D chart. So D is an element of the natural numbers, okay? A D-dimensional chart at a point X is this should be an RD open also. And that is a homeomorphism, okay? That is a chart. And if I have two charts, say phi from ux to vx and phi prime from ux prime to vx prime, two d-dimensional charts are compatible. So this is an important word. That is I'm doing a definition here. Also the word chart, I was doing a definition. Are compatible if, and now I would like to see what happens on the, so if, well, here is a diagram. I do ux intersect ux prime, right? On the intersection, I can go in two directions. This is still an open of my set of my topological space X, and it contains X, right? Because X was in both. I can go with phi restricted to this open to, well, let me say phi of this thing. Oh, yeah, phi of ux intersected ux prime. And this, remember, this is an open in Vx, which is an open in Rd, right? All my inclusions are open. And this I have a phi prime, and it goes to phi prime of ux intersect ux prime. And this is an open in Vx prime. And this is an open in Rd. So on this you could see this is an open subset in R to the D, and you can do analysis on that. That is what you have learned in a, say, a vector calculus course. Huh? And yes?
Could you explain this again?
Can I explain? Again? Yes. But what?
What is ux intersection ux prime x?
I have this intersection, yes.
They're in different spaces, right?
No, this is in one space. This intersection is inside X. Right? The UX is in X. So I have X is my sphere. I will give an example. So here is, for example, my X, right? So let's take a point of the northern hemisphere. I could project it on the XY plane and take the upper half of the Earth there, but I could project it to the XZ plane, and then take the intersection of these two hemispheres, right? That is what would happen. So what that looks like, I don't know, but it is an open subset. Anyway, I say that here I have now phi prime restricted. So I'm not going to put this whole thing here. So phi prime restriction to that subset composed with phi restricted to that subset here inverse. This is, so I can now go from this to this, because these two, this phi x was a homeomorphism. This phi x is a bijective map, and that whose inverse is also continuous, right? It's continuous, the inverse is continuous. So I know that this is a homeomorphism, but I want that this is infinitely differentiable. That's what I want, right? Then I say that they are compatible. And some people just say differentiable, but they mean infinitely differentiable. Infinitely differentiable means you can differentiate it once, and then again, and again, and again, as many times as I like. For example, the sine function, sine of x, x goes to sine of x from R to R, is infinitely differentiable. It's easy because the second derivative is minus this function, so then, yeah, you can go on. But for example, if I take the absolute value function and I integrate this once, then it looks already a bit smooth, but you can only differentiate it once. Because after that, if you integrate the absolute value and then you differentiate, you find again the absolute value, and then you cannot differentiate it at the origin. So this is infinitely differentiable. Also, people call that smooth, a smooth map, right? And what does this look like? This is an open subset of RD, and this too. So this is given by, so here, this thing here, it is given by a bunch of functions, D functions on RD, right? It goes from, so here, a point x1 to xd is sent to, say, a first function of x1 to xd, comma, dot, 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 comma, fd, and then a function of these variables, right? Any point x1 up to xd in this set is mapped to a point in this set, which is also a D tuple of real numbers, and so it looks very concretely like D functions of D variables. And the differentiability, or the smoothness, means that these functions, you can take their partial derivatives as much as you like, again and again and again. Okay? That's what it means. Actually, I should just put these away. Okay, so that is what it means to be compatible. And then the analogy with the Earth is really good, because the next term I want to talk about is of an atlas. And an atlas is really what you have for the place where we live, right? So an atlas of X is a collection or a set, let me just not be vague, is a set, say calligraphic A, maybe, well, these fonts, yeah, let me see, is a set A of charts, D charts. So a D atlas, a D-dimensional atlas is of D charts where the union over that cover, let me say that just like that, that cover X, right? Because I said at a point I know what it means to have a chart. If I have charts everywhere, I want to have a set of charts that in every point is contained at least in one of these U-axes, right? I want to have locally you can say such a phi identifies a piece of my manifold with an open subset of RD. And then we know how to work with it. That cover X. And O is a set of compatible so they should be compatible. And that means that if I look at a point of my manifold in some neighborhood with one chart or with another chart, things that I do should not matter, should not depend really on the chart. I could compare what happens in different charts with this differentiable map. Yeah, so, and yeah, we say that a manifold, a differentiable manifold is a topological space X with a given atlas. Okay, that is what a manifold is. There are certain little problems with this definition. If you look, so in the old days, even now, you can buy an atlas of the Earth, or you would download it. And there are different atlases, but they are compatible, I hope, right? And so if two atlases are compatible, you could also take the union of them. You could take the charts from one atlas plus the charts of the other atlas and put them together in a bigger atlas. And some people like to take a maximal atlas. So they say what you can do is, given one atlas, you can look at all the charts that are compatible with all the charts in your given atlas and just add it to your set. And then you get kind of horrible objects because these are not, atlas doesn't have finite charts. But still can do that, and then that's what in the lecture notes also happens. What I should do is, this is much more important. What I want to do is the next thing is, what maps between manifolds do we want to consider? Right? So now let Y and B be also a manifold. So now I have two manifolds. Then what can I do? What do I want to do? I want to look at which maps from X to Y are differentiable. I want to make a definition of which maps from X to Y we want to work with, we want to allow. When we look at functions from R to R, you say there are good functions and there are bad functions. And the good functions are the smooth ones, the ones that you can differentiate as much times as you like, as many times. And we want to do the same here. Which are the differentiable maps from X to Y? Yeah. The sound is going up. Somebody is playing with the, no? Okay. And F from X to Y, a map. F is called differentiable. Differentiable if, well, let me say, how can I say this the quickest? Let me first say a point x in x. There exists, well, let me say for every chart, D chart, well, this is maybe, oh, I should say also y has a dimension, a manifold. So this is a, say, an E manifold, because there is no need that both have the same dimension, okay? So for every D chart, say phi from ux to vx in B, in I have a chart for my this, and for every E chart, well, u, v, w, x, w, oh, f of x now, to z fx, right? So in the B, some map now has to be differentiable. So, oh, and I want to, of course, let me see. Oh, a continuous map. So my things are already topological space, so it is better to ask that my map at least is continuous. And then I know that the inverse image of Vx, no, the inverse image of W fx, maybe I do a little scratch paper here, because, or I try to make visible to you what I'm thinking and not writing. So what is the situation here? I have x goes to y. Here I have f. Here I have an open. I have two opens here. I have my ux, and here I have an open w of fx. And I can take the inverse image. I want to do f inverse of w of fx. This is also an open subset here, because f is continuous. That is what topology does for you. And then here I can look at the intersection, right? Here I have ux intersected f inverse of w of fx. That is contained in here and contained in there. And here I have my phi x to the vx. Sorry for the complication, but it is this is how it is. It is not simpler. And here I have a map. So actually, this f brings this intersection to that, right? This is still to this subset. And here I have the psi of fx, right? To the, where is it? Yeah. Well, I even don't know if there is a phi, then here there is a phi x, then it should be psi of fx. Goes to, I think it was z fx, and this is in R to the E. And now I can do, and this is homeomorphism, right? Okay, I can say, well, this goes to this phi. I can restrict it to this open subset. So here I go to phi of ux intersected f inverse w fx inside here. This is a homeomorphism. Yeah, so I can invert it. It's invertible. It's bijective. I can do so let me write phi x restricted to ... to this set. I can now make a map from here to here, you see? And how is this map? First do this thing here, but inverse, right? So I do phi x restricted to this open set inverse, and then I do f restricted to this set, and then I do the psi fx restricted to, no, that I don't need to restrict, and this goes from here to there. And that is a map from an open subset. This is an open subset of Rd. So this also, this is contained in Rd, it goes to Re. So it is differentiable. I want that this map should be differentiable, is differentiable at, well, at the point where x goes, right, at phi x of x. So this is a very long thing, and you should not try to remember it by heart. You should just do as I do. Not try to remember by heart, but to say, what is it that we want? And then it is natural to parameterize somehow locally my manifold, and these parameterizations are these phi x's or their inverses, and that's how things work. And so everything has to be, so if you have a map from a manifold to a manifold, and then you have a point here, you take a chart at that point, and you look at what it does in terms of the chart. And the same you do with the image of the point. You also take a chart and you look what happens, and that's the only thing I did. But contrary to physicists, they would just give you the words, but I write everything. Yeah. So it makes sense, it becomes very long. Okay, this is differentiable. So what is my, I think it makes sense now, right? It says map, then f is differentiable at the point for every at this. This map, so this is where the sentence continues, is differentiable at that point. Okay? And differentiable means as many times as you like. So what does this function, what does this map look like? An element here is an element in R to the D. So you have this thing is given by we have here e coordinates, right? So the target, a point here, has e coordinates. So it is given by e functions of d variables. That is what it does. Okay. And yeah, so you want that that every of these functions is as differentiable. You can take partial differentials as much as you like. Okay, then I see that I am behind schedule because the next thing is tangent maps, right? Or actually, and before you have tangent maps, you have to have tangent spaces. So what we want is a tangent space at every point of the manifold X, we want a vector space that is the tangent space. And we want to have a natural definition of it. So, and I even forget the notation. For me, it is Tx at the point X, okay? The lecture notes may have a different notation. And if you open any book, it may have a different notation. We want to have the tangent map, so Tf at X is my notation for the tangent map, and it goes to Ty of Fx. Okay? That is what these are supposed, this is a d-dimensional R vector space, and this is a e-dimensional R vector space, and I still have to give you the definition. right? And so so the elements in this vector space are called tangent vectors. And I think if we take the two-sphere in R3, you know how to do that from your calculus classes. But you see, the problem now is we are doing an abstract notion of manifolds, which is very valuable. But so I cannot use your calculus definition. I have to do something else. So, so what you do is Txx, x, I hope I have enough space here. Maybe I just erased, I will do it on the other blackboard. So the idea is to look at curves that go through a given point x and look at the set of those and divide out by some equivalence relation. That is the cheapest way to get the tangent space of an abstract manifold. So, so here comes Txx is the set, and now I want to do this. I want to say, well, you do, say, a gamma from a small interval, say, minus epsilon to epsilon. This is inside the real numbers, and epsilon should be a positive number, positive real number. This is the open interval. Eh? So I go to x, such that gamma of 0 is my point x, okay? So I could draw a picture of this, eh? So you should draw a picture in your mind of this. I look at the curve, but this curve should be continuous, at least because I have a topological space here. This has the topology from the real numbers. This is a topological space, but I also want it to be smooth. So, and that I have to, such that every chart, D chart, phi x in, say, from ux to vx, and this is in Rd, in my atlas A. Now I have, again, resort to some stuff of the similar kind here, but not as complicated, I think. So I have x, right? I have, I should not put it here, I have my interval minus epsilon to epsilon. I have my gamma, it goes to x. And here I have a subset ux. And so here I have, oh, I want that, okay. In A, well, with that interval, I want that this gamma of t is inside ux, okay? I can say, well, here I have I want curves that go into one chart, right? If necessary, I just make the epsilon smaller, right? That is because this is a continuous map. The inverse image of my chart of this ux will be an open subset that contains the 0. So if epsilon is small enough, then my interval is contained in that open. So I can ask this. And that makes my life a bit simpler because it means that I don't need to do what is there. I have this subset ux, and my map factorizes through this subset. Actually, what I wrote here in formula means in the diagram that the map actually goes through this subset. And now I have my phi x goes to Vx in Rd. I want that this phi x composed with the gamma. Oh, actually, gamma. Yeah, I want that this is, oh, I could have said that. Okay, phi x composed with the gamma is differentiable at x, okay? So, but I could have said that already, right? Because I did already introduce the smooth maps between manifolds. So I could just have said, okay, so continuous and smooth, because that was of differentiable. We have already introduced that. And smooth, and then this can go actually. Sorry for that. But I can use that for my and smooth. Don't cross out everything that is in your notes. I want to divide out by an equivalence relation. So let me like that. This is an equivalence relation. So I take these smooth curves that send 0 to x, and each of these smooth curves defines, what do I want to say? I want to say when two of them are equivalent. And the two, we want to talk about the tangent vector of this curve at the point 0. What does it? So imagine that you drive your car on the earth. Then at every moment you have where you are, you have a direction and a speed. And that is the tangent vector, right? But to see whether if I drive my car at some given moment and you, we have the same direction and speed, we have to express that in a chart, right? So here gamma and gamma 1 is equivalent to gamma 2 if and only if for a D chart phi x ux to Vx in Rd at x, well, in A, I want that the two maps have the same derivative, right? So I can do phi x composed with gamma 1, and I can take the derivative at 0. This should be phi x composed with gamma 2, derivative at 0. And these maps, so the gamma brings you from the real numbers to the manifold, but the phi, the chart, brings you back into Rd, right? And so this map, phi x composed, say, gamma 1, goes from minus epsilon, epsilon, maybe a smaller one, I can always shrink the epsilon, to Rd, right? Because I go, and so also for the other one. So here the derivative of my differentiable map at 0 is a vector in Rd, right? This is in Rd. This is also in Rd. And that is the tangent space, right? You take these things up to this equivalence, and this looks like a horrible definition because this is a very big set, but it is proved in every text on these things. This is a d-dimensional vector space in a natural way. So actually, as my time runs out, let me just go to section 2. But we want, but before I do that, let me say that we got what we wanted. I wanted something, and now I have it. Because I have defined this set, right? Oh, and this, I also wanted this to be a linear map, right? Linear map. And what do I do? If I have an element here, it is the equivalence class of some curve gamma, right? There is every element in such a set modulo an equivalence relation is represented by some element in the set, so there is a gamma, and I send that equivalence class to F composed with gamma. So that is a map, is a smooth map from the interval to the other manifold Y, right? And it sends 0 to F of gamma of 0, that is gamma x. So that is an element in this tangent space. And of course, I skip some things. I don't explain why this is well defined. You should show that if you have this represented by gamma, but also by some other gamma, that these images are the same. But all that you read for yourself in the notes. So then I have a few minutes. I have still 3 minutes or so, right? Yeah? Okay, good. So what is a Lie group? Well, anyway, I will have to confess to Intan that I didn't do my thing. Lie group, section 2. Lie groups. So a Lie group is a group G. Okay, so if I remember well, that on Monday I started with the definition of a group, so you still remember that. It is a group, but a group is just a set with a composition that with G is a group with G also where and at the same time and G is a group G, and how do I say that? And where G also is a manifold, so right, so it should be a group, but also a manifold. So it should have a topology and an atlas, right? Is a manifold. So G has a topology. An atlas. Such that the group operations are differentiable maps. So the composition, the group operation is a map from G times G to G, right? And we could write that as dot, right? This is the multiplication map from the group. And also, I have the inversion map. So let me write inverse, right? That brings an element to its inverse, right? This dot means that is where you put the element. It's called a placeholder or something. Okay? These two should be differentiable. Yeah? That's the definition of a Lie group. Okay? And what will be shown soon is that the TG of the tangent space at the identity element. So we will give examples of Lie groups, right? So the GL2 of R that we have seen a lot is a Lie group, for example. But the tangent space of a Lie group at its, this is the neutral element, has a nice structure. Lie algebra. And now my time is out, but I'm happy that at least I dropped the term, Lie algebra.